Well, all right, looks like we can get started. Welcome back, folks that will be watching this video later on. For today's announcement, major one is that we're going to have our third exam next Thursday. Excuse me, that's a mistake, not next Thursday, but rather next Tuesday. Let's fix this right away before we get started. Our third exam will be next Tuesday. That was an odd mistake to make at the very start. This exam is only going to go up to section 8.6, which the number 10 quiz is based off of, solving square root equations. Starts off in chapter 7. This is finding excluded values. 7.4 is solving equations involving rational functions, where we first would find the excluded values. And most of chapter 8 up to this content here is dealing with simplifying square roots, culminating in this section, solving square root equations. So we could have gone a little bit further since we've also completed sections 8.8, 9.1, 9.2. I felt like cutting it off right here at 8.6 kept the exam 3 size manageable. So that way we're not overloading all the concepts on the third exam. Now what I'll be doing on Wednesday morning is sending out a reminder for everyone to schedule your exam. I sent out a message in the Canvas system here, so you can see it on the inbox for information on scheduling your exam. And hello, Manny, welcome to the class. We're just going over the announcements for the YouTube recording for folks that are going to be watching this later on. Major thing we're talking about is the third exam. It's going to be next Tuesday, involving these sections here. And I sent a message to the Canvas system on how to schedule your exam based on which campus that you're going to be based on. Other announcement we have is quiz number 10 is going to be due Thursday. And we're currently in section 9.3, working through the quadratic formula. But any questions at all before we get started? Okay, well, where we're at so far is the quadratic formula. I feel like before just jumping into this section, it's good to kind of take an inventory of everything we've been solving that's been a quadratic equation, because we've been spending a lot more time on this than it might seem like. This first came up in section 6.5 after discovering our factorization techniques. We applied those techniques to solving just this kind of equation. The quadratic equation just means the highest degree is degree 2, so it can be expressed in this kind of form. In section 6.5, that's exactly what we were doing. It didn't start off in that form, but after we expanded the left-hand side, collect all terms to the left, this is the form ax squared plus bx plus c. Then we solved this one just by factoring it. This one factored nicely. Set the factors equal to 0 and solve. It doesn't always work out nicely this way, so we needed other techniques to help us out. And that's what the section 9.1 was all about. When we have the square root property, sometimes these equations can be solved in a totally different way. If you move the 49 to the right-hand side and you have a completed square, really all you have to do to solve this one is take the square root of both sides. Part A would have worked out just fine by factoring if we did the same technique as in section 6.5, but part B would not have. The solutions are more complicated. There's no integer values to this. So factoring this equation would have been a nightmare. We're not going to get nice results like we did on this one here. This one factored using integers. But this new equation, if we tried to factor it, you'd have to use numbers like square root 66, because these are the two solutions that came up. So suddenly the square root property becomes a major technique, and it required on having a completed square right here. So that's why we went to the next section, 9.2, on the whole completing the square technique. It tells us what to do if there's not a 4z plus 1 squared in the problem, or there's not a 2v minus 5 squared in the problem, and so on. So we studied this as a process. We can transform the quadratic function like this one, rather a quadratic equation, by first forcing the leading coefficient to be a 1. That's why we divide by 2 to start off. Then step 2 said move your constant terms to the one side and keep your variable terms on the opposite side. So that's why we took this 1 here and subtracted it over to the right. Then the magic thing with completing the square is the b over 2 squared form portion. The b coefficient is this -8. When you divide it by 2 and get 16, add 16 to both sides of the equation, and you get this x minus 4 squared. And suddenly it's a problem just like in the prior section 9.1 using the square root property. You just take the square roots of both sides of this equation right here, solve for x by adding 4 to both sides. These are the two solutions that you get. And again, this is a long way we've come from. If we try to do the same things we did in section 6.5, trying to factor this quadratic in this format, it wouldn't have worked out so well in this problem because the square root 15 is part of how you would factor this one. But completing the square does take some time. It's going to be a technique we use later. And this is the purpose to finally section 9.3. If you complete the square, step 1 through 5, on this equation where you don't say what a, b, and c is, you get the quadratic formula. So that's what we're going to be looking into next. So that's meant to be just kind of a quick review on the quadratic equations that we've solved so far, just a warm up and a refresher, before we jump into section 9.3. Any questions with any of those problems before we go into that section? Okay, so here is finally the quadratic formula. First, let me close these files so that computer doesn't get overloaded. So it starts off with the quadratic equation, the ones that we were wanting to solve on the very start. Ax squared plus bx plus c equals 0. If you complete the square on this equation, this is what x turns into each and every time. It has this complicated looking format, but this is what we're referring to as the quadratic formula. It's the solution to this quadratic equation. What makes it quadratic is a is not 0, so there's really an x power 2 term. To solve this equation, well, first thing you'd want to do is just write down the format after you find out what the a, b, and c portions are of the problem. But the very next thing we would do is compute the discriminant. Really, we often do this formula in chunks. The first big chunk is find out what the discriminant b squared minus 4ac is. The next big chunk is just to take its square root, simplify that square root as much as possible using the ideas in chapter 8. Then the third big chunk is just to put it all together with the remaining formula, the negative b plus or minus that square root divided by 2 times a, where the a, b, and the c that we mentioned are these coefficients here. Critically, you have to have 0 on one side, so your quadratic equation must be written just like that. That's what's going on in part A. And then, as a formula evaluation, we can get the solution in a really fast way. This would work for all the other problems we've solved that have been quadratic, but sometimes factoring is faster. So if you notice something factors, it's a good thing to do. A lot of these problems aren't going to factor nicely, so the quadratic formula is what we really would need on this. So that discriminant is extra special. It controls the number and the nature of the solutions that you're going to get. So we have a bit of a trichotomy that occurs. If your discriminant, b squared minus 4ac, comes out as positive, then you get 2 real number solutions. So we see this on a good amount of the problems that we're going to see. But what if it came out as negative? If b squared minus 4ac is negative, this is where we turn to section 8.8, the complex number system. Let me resize this real quick here. This doesn't drag over too easily. Hang on. There we go. So if you have a negative discriminant, that discriminant's going inside the square root. And that's where we're going to be using the imaginary unit I. So this is what we mean by complex number solutions. I enters into the problem because we have a negative root. And this is where we'd be doing stuff along these lines. If the discriminant was -7, this whole square root portion right here, we would just write in as I root 7. So that'd be part of our solution. So far, the bigger than 0 or the less than 0 is telling us positive for discriminant is 2 real number solutions. Negative as a discriminant means two complex number solutions, or by complex, we're picking up I equals square root to -1. And this is the odd case, the one that doesn't happen as often, but can occur quite a bit, potentially in the problems that we'll see on these notes, homework problems, and even exam questions. If you get exactly 0 right here, that means the square root portion that you're going to add and subtract to get to the two solutions is just completely gone. And that's when you get exactly one real number solution. So it has to be exactly equal to 0 there. So that's the entirety of the quadratic formula. Our whole goal next is just to practice working with this, and in particular, pay attention to what's going on with the discriminant. So let me take a quick screenshot. We'll work with this, walk with it down as we go through the problems. And part A is our first equation to try. It's annoying because right out of the gate, part A is dealing with fractions right away. If you left it in this form, the quadratic formula is going to work out just fine, but everything you calculate is going to be just a little bit more annoying dealing with the fraction arithmetic. But because this is an equation set equal to 0, you can work with this equation. You can simplify it, you can manipulate it. We want the equals 0, like we see here, to get the right A, B, and C value. But you could just multiply this whole thing by 11, clear the denominator, and you get a much easier equation to solve. So that's going to be our first step. Let's take the original equation, 2 11ths x squared, 3 11ths x minus 7 11ths. Multiply the whole thing by 11. You have to multiply the right-hand side by 11 as well, but that's no big deal thanks to the 0 there. And then on the left, all you now have is 2x squared plus 3x minus 7 equals 0. And this is a much easier equation to solve. Quadratic formula tells us that the solution is going to look like this. X equals -b plus or minus the square root of b squared minus 4ac, that's the discriminant part being square rooted, divide by 2 times a. So next thing we need to say is, what is the a, b, and the c in this problem? But following the format, right here at the very top, a is the leading coefficient, the one multiplying x squared. 3 is the term multiplying x. That's the b rather. B is the 3 that's multiplying x. And c is -7 itself. So a, if we write this out, is 2. B is 3. C is -7. So all we have to do is plug all those values back inside here, and we'll be on our way. I want to change the color coding just a little bit on these. Next thing we do is actually compute that discriminant, b squared minus 4ac. So let's write this out on the margin. B squared minus 4ac in this problem is going to be square root of 3 to start, so 3 squared, minus 4 times a, which is 2, times c, which is -7. So we just substitute in the 3 values here. Simplify this as much as possible. We have 9 plus, well, this is now positive, so plus with the 2 negative signs. 8 times 7 is 56. So we get altogether a 65. So that's our discriminant. Plugging that back inside here, let's scroll just a little bit. X is now equal to negative of b, so that's going to be -3 in this problem, plus or minus square root of the discriminant, which is 65. Then divide the whole thing by 2 times a, so that's going to be 2 times 2. Where follow the color coding to see where the a, b, and c over here went, down to that -7. All we have to do now is just simplify this as much as possible. This is one of the things that is a little bit trickier in this section, 9.3. We can have the right stuff here, but if the square root simplifies and we didn't simplify it, we might not complete the problem. We might be told to try again simplifying. If the fraction simplifies, we have to do that as well. So first, let's look into the square root. Nice thing about 65 is 5 divides it going in 13 times, but 13 is a prime number. That means these are the prime factorizations, no repeated factors, and square root 65 is simplified. So that kind of reduces our task. That means when we go to calculate this out, x is now equal to -3 plus or minus the already simplified root 65. The whole thing just simplifies further by dividing by 2 times 2, making it a 4. So this is our answer. This qualifies for full credit in a quiz problem or an exam problem. But in the homework system, we've mentioned this before in the last section, Newton makes us separate these answers according to the plus or minus. So the official answer you'd write down in the homework is x is -3 minus the square root of 65 fourths. Or the other solution is that it's -3 plus the square root of 65 divided by 4. And that's one down, our first problem for the day. Any questions on tackling this one? Okay, other thing to mention here is, notice also what happened. We had that the discriminant was positive, which meant we had 2 real number solutions as a statement here. Over here, we have a positive value. This is greater than 0, which implies 2 real number solutions. And that's exactly what we got down below here. Both of these are real numbers because what's inside the square root is a positive number. In other words, we never use the complex unit I itself to get the complex number solutions for this portion. So let's try out another one just to see how these can go. The rest of these notes is really just more about practicing new kind of problems, getting a good feel for how the quadratic formula goes. And then in the next section, we'll look into application problems using these ideas. First, let me put the discriminant down here just for easy reference. And next thing that's kind of challenging with this one is, as a very first step in using the quadratic formula, we must first do the following. First, write the quadratic equation in the form ax squared plus bx plus c equals 0. So we need to actually expand this factorization, get 0 on one side. But while we're looking at this one, let's think back in the day in section 6.5, how nice some of those quadratic equations were. In section 6.5, just as a really fast review problem, we solve v times v plus 6 equals 0. Maybe not that exact example, but something very similar. And that equals 0 is really, really nice when you recognize it. It means there's no big deal with this equation. You don't have to worry about distributing v into the group. You don't need the quadratic formula whatsoever, although you could use it and get the right answers. It's not necessary. This equals 0 tells us use the 0 product property, which tells us the only way this equation is going to check as true is if v equals 0 or v plus 6 equals 0. That was meant to be a highlighter. Let me try again. 0 product property tells us the only way 2 factors multiply, or more than 2 factors multiply, resulting in the 0 is with if one or the other factors are 0. So the solution set on this one was just 0 and -6. So now if you change that up and put in a -11, suddenly it's a much harder problem. This is where we would want to use a quadratic formula. And the reason for mentioning this is, if this wasn't the final exam question, You wouldn't want to waste your time using a big hammer, a big tool to solve it. Quadratic formula works, but it was meant to be solved instantly rather. So if you solve this problem, this is when you know, maybe try to factor it, but this is likely going to be a quadratic formula problem once we expand it and get into this format here. So after seeing the review problem, let's actually start expanding this out. Let's undo the factorization. This becomes v squared plus 6 times v equals negative 11. Add 11 to both sides, and we have v squared plus 6v plus 11 equals 0. And we should always think, could it factor? Because if there's a nice factorization to this one, you still don't need the quadratic formula, and it's still a pretty fast problem. But that's not what happens on this one. This one looks like, because of the prime 11, there's no way we can get it to factor nicely and cleanly like we did, say, all the way back in section 6.5. Let's just take another look at that since it's relevant as a review topic once again. In section 6.5, this was the nice problem, since once we got it to equal 0, with that 24 there and the negative 2 here, this one factored really, really nicely. So when you recognize that, you save a lot of steps and you don't have to use a quadratic formula. But if you did use the quadratic formula on this one, I mean, it's no harm done, really. You took a little bit extra time if this was a final exam question, but it's just not like you're going to get penalized on that. You'd still get full credit. But if you see a good shortcut, the advice is always take it. I don't see a good shortcut on this one due to that prime number 11. So we're going to hit it with the quadratic formula instead. First step is just write out the quadratic formula. It goes, well, if the variable is b, it'll be v equals negative b plus or minus square root b squared minus 4 times a times c, divide by 2 times a. Next thing we want to do is identify the a, b, and c in our problem. A equals, b equals, c equals is what you might write out for that next step. A is always the leading coefficient, and note, we don't always write this in, and we won't do it always on these notes. Let's do it just at least this once, just for emphasis. If there is no coefficient apparent on v, it implies the coefficient is actually a 1, and that's the a coefficient in the problem. So a itself is 1, b is positive 6. If that was a minus 6v, we'd have put a negative 6 here instead. And the coefficient c is just positive 11. We typically write in just 11 without the sign. So once we have the a, b, and c, the next step in this process is compute out that discriminant. So b squared minus 4ac is just substituting in these 3 different ingredients into this format here. So we get 6 squared minus 4 times 1 times 11. 6 squared is 36. This is a glorified negative 44 when we multiply it through. So this turns into a negative 8 altogether. And that's kind of weird because remember, it's going inside a square root. So we're about to take a square root of a negative number. That means the solution to this equation is not a real number. They're non-real numbers. In fact, there's 2 solutions. So we're in this particular outcome down below here. So just for emphasis on that topic, the discriminant b squared minus 4ac is less than 0. So this implies 2 complex number solutions. That means a complex unit, I equals square root to negative 1, is going to come into play on this problem. So doing this in chunks, first get it set equal to 0, extract the coefficients, compute the discriminant, and then plug that value, negative 8, back inside here. So on our next step, b equals, let's start plugging in the rest of the information. Negative b becomes negative 6. So one substitution there for b. Add or subtract. Square root of, the discriminant came out as a negative 8. Divide by 2 times a. And a in this problem is just a 1, since we see just a 1 times v squared here. So we need to simplify this down. Next thing we do is simplify this whole thing right here. Let me change that color coding just a little bit. Let's maybe just leave it like that. So square root of -8. First, due to the negative sign that's here, with section 8.8, we know to write in an I, where I equals square root of -1. So that represents the negative part of the root. We also have to simplify the square root of 8, so we can factor this as 4 times 2. So this is the rest of chapter 8 working for us. This can split as I root 4 times root 2. The root of 4 becomes 2, so it's 2I square root 2. So in this entire thing right here, we're plugging in 2I root 2 altogether. So we're just about there. In the next line, we can say b equals -6, add or subtract 2I root 2, divide by 2. And finally, this is one of those problems where if it was an exam question or a quiz question and you stopped here, you could lose some points. Not a whole lot. You'd probably get a lot of partial credit getting to this step. But in the homework problems, we could miss this question because it still simplifies. Notice the two terms here, 6 and 2, have a greatest common factor of 2, which would cancel with the denominator of 2. So we can rewrite this as, let's factor out 2 from the top. 2 would leave behind -3 plus or minus I root 2 divide by 2. Next, we can cancel these factors of 2 and get to -3 plus or minus I root 2. And that tells us all together, our big conclusion is v equals -3 minus I root 2, or we just use a comma to say or, -3 plus I root 2. So when we said two complex number solutions, these are specifically the two solutions that we found. Well, we did it. That's the rundown on this one. This one was a little bit trickier because we had to put it in this standard form, getting the 0 on one side, and the discriminant was negative, so we had to recall negative square root of 8 involves the complex unit I right here. Well, any last questions or thoughts with finishing up this one? Okay, well, these are some of the main problems we're going to see so far. We have a couple more scenarios of just what else can happen in this section. So the rest of this is just more practice with the quadratic formula. So here's our next one to try. I feel like every one of these problems needs a blank page, so let's just push this down to the bottom. And try out this brand new one. This one looks nice. You could just feed this immediately into the quadratic formula and get a good solution out. It's already put in the nice form where 0 is on one side. But there's a special observation you can make about this one. 64 is always kind of a suspicious number when it comes into play. That's 8 times 8, so it's a perfect square. So it might make you think, maybe this just factors as a perfect square as well. Let's try the factoring on this one. X squared can split as x times x. 64 is 8 by 8. We should pick negatives because of this negative sign. So go -8, -8. And if you were to check this, foiling out to get the middle term -16, x times -8 gives us -8x. Here we get -8x again. Summing those together gives us our -16x. So that's a complete factorization. We could simplify it and just say x minus 8 squared equals 0. But either way you look at it, it's a zero product property result. The only solution to this is if x minus 8 itself is 0. So x equals 8 is the solution. And we are done on this one. All this one needed was a little bit of factoring, and there's nothing more to do. Let's call this method one. Really what this problem is about is just a reminder that whenever you can factor, it's a great idea, because look how much work you can put down when it doesn't factor. Quadratic formula is a lot of work. And if you apply the quadratic formula on this one, it also is a lot of work. So recognizing the factorization is a good idea. Let's say method one, factor. Doesn't always work, so that's why we have the quadratic formula. And just for the sake of practice, because I mean, this is a section on the quadratic formula, let's actually use it on this one and call it method two. This one's the preferred method, so let's also emphasize that. This is the preferred method. And for the sake of practice, let's emphasize, for practice only, let's also use method two, quadratic formula. Notice that one part of the quadratic formula with the discriminant specifically, we still haven't seen. We've seen two real number solutions, that was part A. We've seen two complex solutions in part B, but this one had one solution. That's why we said the solution using the definite article. We haven't had this case come up when the discriminant is identically equal to 0. That's what's going to happen on this one. Let's copy it down to get some clean space here to work with. So my claim is, if you run this through the quadratic formula ringer, your discriminant must be 0. So let's check that out. First, a good strategy with the quadratic formula is just write it down. It's going to help you memorize it. You have to evaluate a pretty big looking formula, so it makes the evaluation part, plugging in all the information, a lot more accurate and cleanly done. So I encourage you to write out this step. X is negative b plus or minus square root b squared minus 4ac over 2a. Just the act of writing that down lets your subconscious think about the problem. So your brain's working as you're writing this down. And the more you write this down, the more it's just going to become second nature working with this formula. Next thing we do is identify the coefficients. In this problem, because this is just x squared, we can think of that as a 1 times x squared, and that gives us the a. B on this one is negative 16, and c would be 64. So there's our coefficients. I'll highlight these just for emphasis. That's our b coefficient, and the 64 is our c coefficient. Next thing we do is compute the discriminant, b squared minus 4ac. B squared, we need to be careful with this one, the calculator. The way we must write this in is as a negative 16 squared, where the parentheses are vital. If we didn't do that, we might get the wrong thing in the calculator. And this was something we discussed way back in the land of exponent laws when we were first looking into these things in chapter 5. Negative 16 squared comes out as positive 256. We are expecting a positive number because b to power 2 for any number b is always non-negative. If you write it this way in the calculator, and maybe you weren't thinking about it, that this had to be positive, you might have accidentally used negative 256, which would have given us the wrong result. So the big warning here, especially when b is a negative coefficient, this always is positive, and writing it down correctly, inputting it correctly in the calculator, does require those parentheses from these two different things we see already. So next part is minus 4 times a, which is 1, times c, which is 64. And well, while we have the calculator pulled up, let's just put this all in the calculator. Negative 16 squared minus 4 times 1, that doesn't really have to go in the calculator. We know it's just negative 4, but just for the sake of matching up what your calculator might look like, here it is all typed out. This is really just 256 minus 256. So it does indeed come out as a 0 altogether. So because it's equal to 0, that's the second possibility down here. This tells us that there is exactly, by the second bullet point here, this implies one real number solution. Already this is kind of interesting in a certain sense. Notice it's impossible to get exactly one complex number solution. They always, as complex numbers, occur as a pair of solutions. But for real numbers, there could be exactly one or two distinct real number solutions for a positive discriminant. And the reason there's one solution is we're plugging 0 right inside here where the discriminant was in the quadratic formula. So now in the next step, let's hide the discriminant now that we're through with it. X equals negative of negative 16 plus or minus the square root of 0 all over 2 times 1. This part is also tricky. That negative sign gets inherited down here, but the b itself is negative 16, so there's a double negation that occurs in this problem. Also, a is 1, so the denominator is just a 2. And that's the discriminant we just computed. So this means when we go to simplify this down, the plus or minus is also gone. Plus and minus vanishing is the reason why there's exactly one real number solution. There's nothing that you're adding and subtracting, so one solution altogether. And this just becomes positive 16. Divide by 2. So x equals 8 altogether. That's what we got on the conclusion right above. I think you'd agree the above solution was a little bit more clean. It was extremely direct, just 3 lines. Quadratic formula, even if you skip this line, it's not advisable. It's a good idea to write down that formula. But even if you skip this line, there's a lot to show here. It's more than 3 lines because there's also work on the right, identifying coefficients and computing the discriminant itself. The more computation you have to do, the easier it is to make the simplest of mistakes, like the one we were mentioning with the negative sign right here. So that's why this one is the preferred method. If you've recognized factoring, even if you're in section 9.3, this is always the best route to take. But again, we practice a quadratic formula, also just to see how case 2 can come into play. We saw it from a separate point of view. Any last questions at all before we try out another one? Okay, here's our next one to try. This one doesn't look too bad. Let's hide that one. This is where the revision occurred in the notes. That one will be the last one for the day. And this one really doesn't look too bad in all honesty. There's a fraction in it, but our very first problem did have fractions, so we know how to correct that. Really the big reminder for this problem, the thing we have to be ready to think about is we must first put the quadratic in the form ax squared plus bx plus c equals 0. So that equals 0 part is vital. If we don't have a 0 value there, we're not grabbing the right coefficients a, b, and c any longer. So other thing that's kind of annoying about this one is, of course, that it has a fraction. So we'll do, let's say, 2 things. Let's multiply both sides of this equation by 6, then produce a 0 on one side by doing the right subtraction. So to start it off, let's take 6 times the left side, x squared minus x, 6 times the right-hand side, which is just a 1/6. Distribute in over here, and we have 6x squared minus 6x, and the fractions cancel on the right-hand side to just a 1. Then finally subtract the 1 from both sides, and we have 6x squared minus 6x minus 1 equals 0. And that qualifies for the first thing that we had to produce. 0 on one side. After we have that, let's write down the quadratic formula again, just to prepare our subconscious for what we're about to do. X is negative b plus or minus square root b squared minus 4ac. One common mistake is don't forget that the denominator covers all the way from the negative b to the end of the square root here. So 2a divides everything that we wrote down. But once we have that, we're in business. We have a b, and a c coefficient. So we'll plug those into the right spots. Plug in a value for b here, a value for a here. Then we'll also calculate the discriminant. So really it just becomes the same sort of process each and every single time. So let's write out a equals, b equals, and c equals to start it off. A is 6, b is negative 6, and c is negative 1. So those come from the coefficients here, same as the coefficients we labeled a, b, and c for this generic form of the quadratic equation we're solving. Now we move down to the discriminant portion. This is going to tell us what we're expecting to see. What do our solutions even look like in the first place? Are they real? Are they complex? And how many solutions we'll get. So let's write out b squared minus 4 times a times c. Substituting in the values, we have negative 6 squared minus 4 times 6 for a, negative 1 for c. So simplifying this down, this is 36. This is going to be, excuse me, a positive with the 2 negative signs here. So plus 24. And so this turns into all together a 60. Well, it's a positive number. So we're on case 1 of what can happen with the solutions. This is greater than 0, so we're expecting 2 real number solutions. So now that we've done all that preparatory work, getting the equation in the right format, computing the discriminant, we just plug it all in and start to calculate x. Let me move this down just to get some clean space for us. So x equals, again, watch out for the double negation that occurs again on this one. That negative sign just copies in, but the b coefficient has its own negative coming in. So negative 6 drops in here. Then it's going to be plus or minus the square root of 60, the discriminant we just computed, divide by 2 times 6, the a coefficient. Next thing we have to do with this is we really have to simplify that square root down. So this is now our chapter 8 in action, simplifying square roots. Square root of 60, well, let's first think of how that might simplify. 2 divides 60 going in 30 times, 2 divides 30 going in 15 times. But 15 is kind of where the trail goes cold because the factors here are just 3 and 5, none of which are repeated. So that tells us the best way to split 60 is 60 is, you could write this as 4 or a 2 squared, up to you, times 15. Then it also informs us to simplify square root of 60. We're taking the square root of 2 squared times 15. But here, because the power is 2, we divide by the index 2 and get just a 2 here times the square root of 15. So root 60, by this work here, we can substitute in 2 root 60. And here's what we have next for x. X is positive 6 plus or minus 2 root 15. Another color coding to show that substitution over here on the right. Divide by, you could multiply to get 12, but it's kind of slightly more convenient as just a 2 times 6 at this point. That's because this whole thing is now going to simplify once again. We can factor out a 2 in the numerator and get 2, leaving 3 plus or minus square root 15. Divide by 2 times 6. So these twos will cancel, and all we're left behind is 3 plus or minus the square root of 15, divide by 6. So we got it, folks. This one is kind of a longer one to get through because there was extra work at the very beginning, 3 lines just to get the quadratic equation even put into place. But now that we're down here, this tells us, yeah, there's 2 real number solutions. They differ by whether you pick a positive sign here or a negative sign. This is really just one big shorthand right where the red dot is, but we've been writing it out this way. 3 minus root 15 over 6 is one solution, and the second one is 3 plus root 15 over 6. At this stage, we're done, and that's the complete solution for that original equation at the very top. We'll practice one more just for the sake of getting good practice on this topic before jumping into the next section. Let me close out this file here. But any last questions at all on the solution method for this one? Okay, one last one to try, and then we'll be looking into the next section. Here, this is where the notes got revised. I revised this in Canvas, as well as on the file called Blank Lecture Notes. The revision I had to make was due to, for some reason, when I typed this out, I put the x in this denominator, which did not make sense. And if we clear denominators, it's not even a quadratic equation any longer. So I put x where I believe I was intending to put it in the first place, right here. So that's why these 2 spots are red. So this one's not too bad. You can get 0 on one side really fast just by adding 1/3 to both sides. So we have a third x squared plus 1/4 x plus 1/3 equals 0. And then what would make this equation kind of a tedious one and a nasty one to get through is if we said a is a third, b is 1/4, and c is 1/3. The quadratic formula works, but now it's a lot of work to simplify this all the way down. You'd have to simplify the discriminant, which is now a fraction inside the root. So a really good idea, really for the sake of survival, to make this a doable problem is definitely clear the denominator. Between 4 and 3, the least common denominator is 12. So our next step is multiply all numerators by that 12. So we'll get 12/3 x squared plus 12/4 x squared, or excuse me, 12/4 x plus 12/3 equals 0. Well, it's really 0 times 12, but we know that's 0 as well. That's kind of nice. And this is the thing that's kind of forgiving about the quadratic formula. You can often simplify down these equations, and we'll be taking advantage of that in the very next section as well, when we look into the applications. So 3 divides, giving us here a 4x squared, then it's a plus a 3x, then plus a 4 equals 0. So this is the thing that we'd want to solve. Looking at this, I don't think it's going to factor in a nice way. But one other additional concept is it would factor if the discriminant, this thing comes out as a perfect square. So you can test factorization really quickly on this one. First, because I don't think it's going to factor nicely, let's write down the quadratic formula. X equals negative b, add or subtract, discriminant, b squared minus 4ac, all over twice a. Then we grab the coefficients. Here's a, b, and c. All positive this time. So a is 4, b is 3, and c is also 4. Next step is the discriminant, b squared minus 4ac. So our b is 3 for a 3 squared, minus 4 times 4 for a, 4 for c. And this is definitely a negative number. We're getting 9 minus 4 times 4 times 4 is a 64. So 9 minus 64. That's going to give us altogether a negative 55. And 55 is kind of nice. That's just 5 times 11. So it doesn't really simplify as a root, except when you plug in the negative here inside the root, that'll give us our two complex solutions. So we have to simplify a little bit to show the complex unit I. So this one has solutions, it's just not real numbers any longer. In our next substitution step, we have x equals negative b, so that'll be a negative 3 in this problem for b, plus or minus square root of negative 55 divide by 2 times a, and our a value is a 4 this time. Let's move that out of the way as we go to simplify this. Once we get down to here, we're just about home free, but we do have to simplify this as much as possible. This becomes negative 3 plus or minus. And just a reminder, when you see a negative root 55, we can rewrite this as a I root 55. So I root 55 would plug in right here, coming from the negative sign, we get the I. Whole thing is divided by 8. And that's our two solutions. So the only solutions to this original equation up here are x equals negative 3 minus I root 55 divided by 8, or negative 3 plus I root 55 divided by 8. And we've done it, folks. That's our big tour of dealing with the quadratic function, or excuse me, the quadratic formula. Any last questions at all before we take a look into the next section on applications? No, these problems will not be on the third exam. This one will be on the final exam. As far as the third exam goes, it's going to end in section 8.6, which is solving square root equations, similar to what you're going to be doing in this quiz number 10 up here. I felt like that cramming the chapter 9 stuff into the third exam was just going to be too much because the number of sections here, if I end it right on section 8.6, is about the same length as exam 2 was. I didn't want to write a third exam that was suddenly like 4 sections longer. So exam 3 only is going to go up to section 8.6. Other questions at the moment? Okay. Well, our next section is going to be doing more square root problems. So we'll be doing more practice with this, but now in the context of looking into applications. This one is also our last big application word problem section for the entire semester. So congratulations. It's kind of nice to get through the last one, 9.5. We'll be doing a couple problems today. We'll look into a couple problems next class as well. And looking into next section, next 9.6 in the next class. Well, here's how they go. They're all just pretty simple scenarios that we're going to look into, but every one of these, somehow, some way, is going to involve potentially a quadratic formula. So example 1 is kind of like a warm-up one, nothing too fancy is going on here. Example 2 is something where we have area we're dealing with. So this is a problem involving a rectangle. Then this one is going to be a uniform motion problem, distance equals rate times time. So we're revisiting a lot of interesting results, a physics problem, and then a rate of work problem. This is a similar problem to what we saw in section 7.4. Only difference is this one turns into a quadratic formula situation. So 5 different scenarios. Example 1 is kind of a warm-up. The major idea is if we can get this into an equation, you can make it look like a section 9.3 problem on the quadratic formula, and it really isn't too bad. So the first thing is just to translate all of this information into that equation that we're going to solve. Starts off by saying the sum of two numbers, so added together, is 11. Their product, so those two numbers multiplied together, is negative 2040. Instructions just say, find the numbers. But that means those are the unknown quantities. Those are the things we would label, give a name to. So let's say, just for generic values, X is the first number. Let me write it down in a slightly different spot. Let me put it here. X is going to be the first number. Y is going to be the second number. So those are the variables that we're going to be working with. When it says the sum of the two numbers is 11, we can just take this whole sentence and rewrite this as just X plus Y, so now it's a sum, is 11. There's the actual 11. When it says the product, this just means multiply. So this will be X. I'll put the multiplication there just for emphasis, although we wouldn't often write that down in algebra. Their product, X times Y, is negative 2040. And this is our system of equations to solve. It's kind of like what we did in chapter 4. Chapter 4, we did solve lots of systems of equations. So it's kind of neat to see a topic from back in the day coming into play once again. But this is a little bit different this time. When we're solving system of equations, these were application problems, but same idea. What made this system kind of nice were they were linear equations. Our first equation is linear, and it's basically the same kind of thing. P plus B is like X plus Y comes out as a total value, 284 books on this one. But our equation right here is nonlinear. X times Y makes it very different from this one. This one was just another linear equation. So once you have things multiplying, that's where things get a little bit different. This is where the quadratic formula is suddenly something we might want to use. We can solve this in the same kind of way, use the ordinary substitution method. We could say isolate for the Y variable. Once we solve for Y, we can plug it in over here on the left. Let's make that our strategy. And if you solve for the X variable and plugged it in over here instead, that would work out just as fine. So there's multiple good ways to start this one. Solving for Y, you would get that Y equals 11 minus X. So we can plug that in over here. So now this is the substitution coming in. X equals 11 minus X, now in place of Y. It's equal to negative 2040. And this is the equation that we want to solve. This one's quadratic in the variable X. It doesn't look like it's an easy time trying to factor it because this number is so large to deal with. It may factor, but if you get a huge number like this one, this is another scenario where the quadratic formula is a good idea. Let's distribute X into this group. We'll get 11X minus X squared equals negative 2040. If we're using the quadratic formula, we want 0 on one side. Let's actually get the 0 on the left so we can force X squared positive. Add X squared to both sides, so now it's positive. Subtract 11X from both sides, so now we have a negative 11X minus 2040. So quadratic formula is built just to handle this kind of scenario. We have an A, B, and C coefficient. B is negative 11, C is negative 2040, and A is a 1. A is 1, just as a reminder, only because you could put in a 1 times X squared here just to emphasize it. So with those three values, we can now solve for the discriminant, B squared minus 4AC. Plugging in the B value, it's a negative 11, which we square. Then take negative 4 times the A value, which is a 1, and the C value, which is negative 2040. Because the numbers are so large on this one, this is a good time to just drop it into a calculator. So this will become negative 11 power 2 minus 4 times 1 times negative 2040. And we get 8,281. So that's our discriminant. What we know for sure is, well, that's going to be two real solutions to this. And that makes sense. There's two numbers we're dealing with. So coming back over here, if we write out the quadratic formula, it takes the form x equals negative b plus or minus the square root of b squared minus 4ac, the quantity we just calculated, the discriminant, divided by 2 times a. If we plug in these values, we get x equals negative of negative 11, so that's our first substitution. Add or subtract the square root of 8281, that's our second substitution, the discriminant itself. And all of it is just divide by 2. So now, still a calculator problem, we have to take that square root. So back to our calculator here, let's compute square root 8281. This one came out as a perfect square because the square root is 91. It tells us, for the brave, if you really want to, you can factor this one. Just doesn't look like it's a good time, again, because the number 2040 is so large to deal with. So we'll just put in a 91 right in this position. This equals positive 11 plus or minus 91 divided by 2. So now we have two different versions of the answer. If we go with the minus, it'll be 11 minus 91, so that'll be negative 80, divided by 2 for a negative 40. If we go with the plus version, we'll have x equals 11 plus 91, so that's going to be 102, divided by 2, but then that would be 51. So there's two possibilities for x, which is kind of interesting. We never really had this situation occur. Once you get your two x values, they plug inside here. So the answers are going to be 11 minus your first x value, negative 40. Your second answer is going to be 11 minus the second x value, 51. But notice what happens. There's a weird kind of symmetry in this problem. When we plug both these x values, negative 40, 51, into the equation for y, we get both of the x values, negative 40, 51, in reverse order. Well, if we add these together, we definitely get positive 11, so that checks. We're wondering majorly, if we multiply them together, take 51 times negative 40, do we get negative 2040? And we do. So that tells us this is kind of an odd problem. We didn't actually have to return to y. Oftentimes you do in these kind of problems. But this time, these are the two solutions. We can say here, just to emphasize, the two numbers are negative 40, 51. Let's box this out just to emphasize this is our solution this time. So again, kind of a weird problem. It's meant to be a war bump problem because it's a fast problem to set up and get down to an equation for which you can apply the quadratic formula to pretty rapidly. Other problems have kind of a longer setup. Some problems have an instant setup. There's a lot of variation in these notes. So let's try out the next one just to see what else can happen. If you're watching the video, this is a good time to just pause it to see if you can start to solve this from scratch based off the information we're given. We're told for Sophia's graduation party, several tables of the same width are to be arranged end to end to form a serving table, so a gigantic one, having a total area 70 feet squared. So that's the starting information. The total length of the tables will be 5 feet less than 5 times the width. So we have a lot of tables lined up end to end. This is going to cause a rectangle structure. So Sophia is a fancy person, and this is going to be a part of her graduation party. One gigantic table with smaller tables laid out end to end. We're told that the length is going to be 5 feet less than 5 times the width. So we can write that in for W. We can consider this to be the width. And the area is 70 feet squared. what we want here is to find the length and the width. So this will be the solution to the problem once we find L and W. And it's a practical problem. Sophia wants to know this information so she can purchase the correct tablecloth. She knows that she can spend as much as an area of 70 feet squared, but when she goes to, say, Walmart to have that cloth cut, she wants to know the dimension. All she knows for sure is it's got to be 70 feet squared. So it's kind of a weird problem, but you can imagine it's practical in a certain sense. Next thing you could do to solve this is just write down the area formula. Area equals length times width. We already know that area is 70 feet squared, so we can make a substitution here. I'll drop the units until we get to the end part of the problem. We also can make another substitution for length. Probably shouldn't use that color. That has a different meaning for the quadratic formula. We can substitute length in right in this position for L. So 5W minus 5 times W is the equation we're solving on this one. But you know, it's just like the other problem. This is another quadratic equation in the variable W. If we expand out the left-hand side, we're looking at 70 equals, expand the right-hand side rather, 5W squared minus 5W. Subtract 0 from both, 70 from both sides to get the 0, and we have 5W squared minus 5W minus 70 equals 0. And you can use a quadratic formula on this equation, but you know it's just as easy as dividing both sides by 5 to make this problem even faster. You would get 0 equals W squared minus W minus 14. So the same concept as before, try to simplify the problem as much as possible. Really helps out again on this one. This gives us the A, B, and C coefficients we need. A is 1, B is -1, and C is a -14. But at this stage of the notes, this is again a great spot to be in. All we're really doing is a redo of the quadratic formula problems in the last section. The solution is instantly expressed as W equals -b plus or minus square root of b squared minus 4ac divided by 2 times a. Notice on this problem, we're also going to be rounding to the nearest tenth, so we have to be careful with the calculator on this one. These are good problems to practice with the calculator nearby when you're doing these. Make sure you're using the same calculator that you'd be taking into an exam setting as well for the final exam. Plug in the value for, let me highlight slightly differently, B and A. Well, let's also chunk this problem by doing that part as well, the discriminant. B squared minus 4ac on this problem becomes -1 squared minus 4 times 1 times -14. So this is +1. The two negatives here means we're adding. 4 times 14, that looks like a 56. So this becomes a 57 altogether. So put in the square root of 57 in this spot, and we have W equals negative of -1, so that's one substitution in for B. Add or subtract the square root of 57, that's the second substitution for the discriminant. A is 1, so we can just say divide by 2. That's really the third substitution, but a 1 would go in this spot. It doesn't hurt to write that in, so let's emphasize by putting in that 1. That means when we go to actually round this to the nearest tenth, we'll be plugging this into the calculator. We're plugging in 1 plus or minus square root 57 divide by 2. In your calculator, it's going to look more like this. 1, you'll pick a positive or negative sign, square root 57, put parentheses around that whole numerator, and then divide by 2. So let's see what we get out for W. So first a parenthesis to match up this form, 1 minus square root 57 divide by 2. Our first answer to the nearest tenth is negative 3.3. So that's one value for W. But notice that's nonsensical in this problem. Sophia's going to have the worst graduation party of all time if she goes for a table with a negative width. It wouldn't make any sense. So this problem is going to be eliminated only because it's a practical problem where this is a dimension forced to be positive. Plug in the positive result, we have 4.27, rounds to a 4.3, and that's more reasonable. The width, that's a 4.3, looks like it would make sense. So we eliminate the negative solution, and we have W is 4.3. We want both the length and the width, so we're halfway there. For the length now, just plug 4.3 right here. This would be 5 times 4.3 minus 5. So the length is going to be 16.5. Both in dimensions of feet. So that would do it. The area is not going to be exactly 70 feet squared because we rounded to the nearest tenth. But it's going to be pretty awful close. So that's the solution to a lot of these kind of problems. Write down something that's going to give you an equation and then just solve that equation. Let's try out one more before we close out the notes for the day. This one takes a little bit more time, so maybe not the good one to do next. But I mentioned some of them are set up almost instantly, and this is one of those kind of problems. It says an arrow is shot vertically upward at a rate of 220 feet per second. I don't know if that's someone with a really strong arm or not, but that's the information we're given. Use the projectile formula. Height is negative 16 t squared plus v sub 0 or v naught times t to determine when the height of the arrow will be 400 feet. When we say height of the arrow is 400 feet, again, I shouldn't use that color. Let me use green on this one. That's just plugging a 400 here. And when it says that the upward velocity was a rate of 220 feet per second, that's just what's going to go in place of v naught right below there. So writing this all together, our equation becomes h, we'll plug in 400. Let me get my colors going first. Equals negative 16 t squared plus v naught, which is 220, times t. There's problems just like these in the homework where this is really just the main idea. Substitute in the information in the problem. You immediately get to a pretty fast equation to solve. We can say 0 is negative 16t squared plus 220t minus 400. And like we mentioned before, you can also cut these numbers down to size. You could say divide everything by negative 16, and that would be appropriate. Let's take that strategy. Divide the left by negative 16, the right-hand side by negative 16, and we get the new equation. We're dividing by a negative, so first term flips to a positive. And this might not divide evenly, but 16 is not going to give us a repeating decimal. This will terminate. So 220 divided by negative 16 gives us negative 13.75 times t. It seems awkward, but the quadratic formula doesn't care if it's a decimal number. Fractions are a little bit more tedious, but we're going to round our answer, so we might as well just be okay with the decimal number. It'll give us a perfectly fine value. Next, take negative 400, divide that one by negative 16, and that one comes out as an even positive 25. So now this is our formula to solve. We have a, b, and c coefficient. A is 1, b is negative 13.75, and c equals 25 on this problem. So by the quadratic formula, the solutions are t equals negative b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. So following a pattern that we've done pretty much all day today, we first calculate that discriminant. B squared minus 4ac becomes take negative 13.75, square that result, minus 4 times 1 times a c, which is 25. Let's plug this all into a calculator to get negative 13.75 squared minus 4 times 25 gives us 89.0625. Rounding to the nearest hundredth, let's keep all the decimal places for extra accuracy, so we have a very accurate answer at the end, 89.0625. Now, just like in the last problem, t is time, so this has to be a positive quantity. So we'll keep that in mind when we go to calculate its values. First, plug in the b value. B is a negative 13.75. So we have double negation here again on this problem. Watch out for that part. That's always extra tricky. Plus or minus the square root, 89.0625. So that goes in this position. And divide the whole thing by 2. Let's simplify this a touch. What's going in the calculator is going to be 13.75 plus or minus the square root, 89.0625, divided by 2. And I wrote it in this way as well, kind of a more sideways notation, because this is the way it's probably going to show up when you put it in your calculator. So 13.75 minus the square root, 89.0625, divide by 2. So to the nearest hundredth, our first potential candidate is time. The number of time it'll take for this arrow to reach a height of 400 feet is 2.16 seconds. So 2.16 seconds really has a lot of hang time here. If you put in the plus on this one, it comes out as 11.59 seconds. And this problem is a little bit different. We have 2 candidate answers, but when you think about that, it's because the trajectory of this arrow really looks like this. It reaches a height of 400 feet once when it's on its way up, and that's in about 2 seconds. And then it reaches its height of 400 feet again. Here's the 2.16. When we're at about 11.59 seconds is when it reaches that height again. So this one had 2 values because it's going up, getting it to that height, and then coming down, hitting that height again. So we keep both solutions on this one. Well, that's the adventures with the quadratic formula so far. We left 2 questions on these notes still unsolved, so we'll come back to these when we do them on Thursday's class. So just a reminder, don't forget to schedule your 3rd exam. I'll send out a reminder as well on Wednesday. There's review materials to help study for that exam, version 1 of the review, version 2, and another version on the Newton homework system. But have a great night, folks. We'll be back to this next time.